And this is the topic of the presentation today by Wim. He's very well known in the area. He has been working in the fundamental science of lignin and surface chemistry of cellulose. I can't say this by heart. I don't need to read the bio. He's really an expert in the area of XPS interpretation, and also modeling of surface interactions. I remember that. And then recently, he's also looking not only into cellulose, but also degradation of polymers by different routes. Also, an interesting topic that I learned today is the use of glycosylated triterpenes or terpenes for health sciences and applications. So many common areas that I'm sure you can connect with. I don't want to take all the time just to introduce you, Wim, so I think the floor is now yours. You are very welcome, and to the students at the end, if you have a chance, come to talk with him. Again, on the basis of the science, but also on the basis of leadership. He's the current chair of the American Chemical Cellulose Division, and that's great. And one thing, yes. And one thing, of course, is the fact that we need students, postdocs, graduate students, undergraduate students to volunteer in these activities. Please get engaged with the cell division. That is for your own growth and for the contribution to the community. Scott Reneker, Feng myself have been also very involved in the cell division, and Wim is now the leader there. So welcome, Wim. The floor is yours.
Okay, thank you, Orlando. Yeah, Scott was very happy that I'm the chair because he was the chair before me, so I took over from him. So he's a little bit of less work. So welcome. Yeah, I'll be talking about surface interactions and assembly of cellulose nanomaterials, nanocrystals, largely, and I'm heading the Sustainable Materials Lab at KU Leuven. And for those of you that don't know KU Leuven, it's a university that's been around for a while. It was founded in 1425. So next year we have our 600th year anniversary, and yeah, they've been planning this for years already. So there's going to be big celebrations. We recently were 43rd in the Times Higher Education World University Ranking in terms of size. It's almost 60,000 undergrad students and about 5,000 PhD students. Very interestingly is that the university has 14 different campuses in 10 different cities spread around the Flemish-speaking part of Belgium. So it's a university in Belgium. Belgium has two languages, Flemish, which is a dialect of Dutch, and French in the south. And so this is a Flemish-speaking university. The university has about 124 spin-off companies, and last year, when the last numbers, about €750 million in research funding. So it's a very research-active university. So Leuven is located here. So this is Belgium. You have the Netherlands, Germany, and France, and then a small country, Luxembourg, that everybody forgets about. But here's Leuven. Located in Leuven itself, you have three different campuses and three different locations. And then you see that the locations all spread over the Flemish-speaking part of Belgium. And I'm located at the campus here. Yeah, this is the town, well, the city where I live. And if you come to visit, of course, you're going to have to share Belgian beer. And if the weather's nice, we'll sit by the water and have a decent Belgian beer. Some more pictures. So let's get to actual research. We all know, I think most of you know, the hierarchical structure of wood. So we're not really going to talk about it. We can get these cellulose microfibrils under concentrated acids. We make the nanocrystals. And so without going too much into detail, most people will notice. So then, very important then if we start looking at the structure of these, and that's something people sometimes forget when you start working them. You want to start working with them immediately. You have your glucose unit, and now this should start playing. Yeah, you have your glucose unit, which is arranged, of course, via beta 1,4 linkages to make your long cellulose chains. These cellulose chains are then stacked together into a crystalline pattern. And very importantly, you see that all the hydrogens in these glucose molecules are sticking upwards or downwards. They're all in the axial positions. And all the OH groups are in the equatorial position. So if you look at this structure, you have all carbon-hydrogen bonds going in this direction, and all the hydroxyl groups are within these planes. Why is it important? Well, everybody says, or a lot of people say, that these nanocrystals are held together by hydrogen forces and hydrogen bonding. That's only partially true. All the hydroxyl groups are in the equatorial positions. That means that the hydrogen bonds can only exist in these equatorial planes, so only in the length of these planes. If you look in between these planes, you only have carbon-hydrogen bonds. These are not that strongly polarized, so you only have van der Waals interactions between these different planes. And these van der Waals interactions have nothing to do with hydrogen bonding, but they're absolutely critical. Now, why is this still held together by such weak forces? It's if you look along the long chains of cellulose, you have many of these very small interactions, and the many small interactions make very strong interactions altogether because it's cumulative. Now here, this is drawn as a square cross-section. If you follow the discussions in the field that has been going on for quite some time, it seems like it's getting activated again. You might have cross-sections like this. We don't know yet what the exact cross-sections are or how many cellulose chains there are in the cross-section, but you can have this setup, you can have that setup. And these are especially important because if you see this, then you here get hydrophobic planes because you only have hydrogens sticking out here, and you have the hydrophilic planes on the sides. Here you have the hydrophobic plane there, and you have the hydrophilic planes there. That basically makes your cellulose nanocrystals amphiphilic, where you have hydrophobic planes and you have hydrophilic planes, which makes it very interesting. Now, everybody who's worked with these cellulose nanocrystals, the ones you derive from sulfuric acid, for example, so when you get them charged, we know that they form, you start with, with an isotropic suspension at low concentration. As you concentrate your CNC suspension, they start aligning them and they form chiral pneumatic structures up until the point where your whole volume is taken up by chiral pneumatic structures. This is roughly what it looks like. And we know this happens almost all the time. If you're somewhat careful, it's very robust. It works with CNCs that you get from all kinds of different sources. Your polydispersity is not really that important. It still does it, which in itself is quite remarkable that it's so robust and that you get this assembly. These structures, these aligned structures, we can retain them during drying, so you can get them when you dry your droplets. You can retain them by film casting. You can create 3D assemblies, then dry the system and create aerogels. So we know we can do this, and this is all quite robust. Now, despite the fact that we know this happens, there's still a lot of fundamentals about this assembly or these interactions that we don't know. So what are these? Well, the interactions that control this kind of assembly, the interactions of CNCs with their environments, that's still something that not much is known about it. And once we understand it, we might be able to better control it because these interactions are going to control a lot of the properties of the materials we want to make from them. We don't really know what the effect of dimensional variations and surface functionality is on the structures that you get. We know we get certain structures very reliably, but the actual properties of these structures, for example, the pitch in the chiral pneumatic phase, how that actually varies with these different parameters, we don't really know. We don't have direct models where we can dial it in and say exactly, okay, this is what we're going to get. How this transition between the isotropic and the cholesteric or the chiral pneumatic phase happens with increasing concentration, we don't really know. We don't know much about the kinetics of self-assembly. Normally what people do is we make these systems, we let them sit for 2 months on the shelf, and then we say, oh, this has assembled. I'm a chemical engineer. I don't want to wait 2 months. Right? I would like to do it in 10 seconds if I can. Right? We can't do that. If we do it too fast, it gels, and we don't get these chiral pneumatic structures. So in order to speed these up and to understand what's happening, we need to understand the kinetics of this self-assembly. And then the actual structuring in the chiral pneumatic phase, what does it actually look like? Yeah, we have these pretty pictures here, but is this really what it looks like? Is that really what you have in there? Is that one monolithic phase? if we look at metals that crystallize, we know we have different phases in there. We can have different crystals coexisting. Do we have that there too? We don't really know what this looks like inside. So let's start with these are different points that we've been working on, and I'll be talking about it. So if you look at the interactions, then let's go back to basic first year physical chemistry. Right? So what is surface energy or surface tension? Surface tension is liquid, surface energy is for solids. It exists because basically surface atoms or surface molecules that we have a deficiency of interactions. They don't have interactions or much less interactions with the gas phase above them, whereas a bulk atom or a bulk molecule has an isotropic interaction with everything around it. That basically means that this comes in a higher energy state. These interactions are all based on the interactions that we know, going from the weakest one, the dispersion, London dispersion interactions, based on polarization of molecules, all the way to ion-ion interactions. Now, there's one thing. These are all interactions based on differences in polarity. Yeah. Why is that important? Without polarity, you cannot have interactions. Yeah? Ideal gases have no polarization. If they exist by themselves, that means that they have zero attraction. Why is it important? Well, water is a polar molecule. If water comes in the area of something that's non-polar, it'll polarize that molecule, and they will start interacting via charge differences, by polarization. Water will always do that. Every molecule can undergo polar interactions. That means that something like hydrophobic interactions do not exist. Two things that are non-polarized cannot interact. Yeah? You have zero interaction. Yeah. But we do know that apolar particles will selectively go to apolar solvents. Apolar particles will interact with apolar surfaces. If hydrophobic interactions don't exist, why does that happen? Well, from fundamental thermodynamics, we know that if the Gibbs free energy is less than zero, we have a spontaneous process. This is a spontaneous process, so we need a negative Gibbs free energy. If you want the enthalpy of interaction maximum, you can look up the data of apolar molecules in water, and you will see that their interaction with water is always stronger than their interactions with hydrocarbons, their enthalpic interaction. That means that to get a maximum delta H, our apolar molecule will want to be completely in the water phase and not in the apolar phase. If you look at entropy, to maximize entropy, we're going to have as apolar material or apolar molecule spread around both phases, because that creates the maximum amount of chaos. Now, this is not what we see. What we actually see is that it selectively goes into the apolar phase. Why is that? It's not because the apolar molecule, it's obviously not because it has better interactions with it. It's not because of entropy. It's because of the water. It's the water that governs everything. Because if you have an apolar solute inside the water will structure around it, and it will not be happy because it prefers to have more degrees of freedom. The water does not want to interact with this apolar solute. It does not want to interact it because it can have less interactions with the apolar solute than with other water molecules. The other water molecules are more polar, it can hydrogen bond with it, and it has more degrees of freedom. So the water structures around it to minimize its interaction with the apolar molecule. And what it will do, it'll push out this apolar molecule to increase its own entropy. So basically, it's an exclusion effect, which is governed by water and not by the apolar molecules. Why is it important? Well, it basically means that if you have water present, the entropy of water is going to dictate all the interactions that you have. And so we modeled that. So let's go back to nanocrystals, nanofibrils then. We modeled the cross-section of nanocrystal. It's a nanofiber, but we took the crystalline section. You can model the structuring of the water molecules around it. Then we took a hydrophobic drug, furosemide. You also model how the water molecules structure around it. And if you then do the calculations, you indeed see that the hydrophobic drug is going to selectively absorb onto the hydrophobic planes of the cellulose. Why? The reason is that the structuring of the water molecules around these hydrophobic planes is stronger, is more, because it doesn't want to interact with it than the water molecules around your hydrophilic planes, because there it can undergo hydrogen bonding and polar interactions. So it's the water, by releasing the water that was sitting on these hydrophobic planes by the adsorption, that the net effect is that these water molecules will gain a lot of entropy and will actually decrease the Gibbs free energy as it absorbs. From this modeling, we got Gibbs free energy changes of adsorption of between minus 19 and minus 26. That's from modeling. Remember that value, it'll come back later. Where else do we see this? Well, if you take CNCs after extraction and you do the normal process where you do your centrifugations, you do your dialysis, then you dry it and you do elemental analysis and you determine the carbon content. Here we show two different batches. If you don't have any extraction, you get carbon contents of between 41 and 42%. Whereas if you do the theoretical calculation for pure cellulose, it should be a little bit above 44%. That's a big difference. If you don't have that, it basically means you don't have pure cellulose. Whatever you have here is something else. So we then did extractions with different solvents, and I'm showing only 4. We've done a lot more. And you see that you increase this carbon content. So that basically means you're starting extracting compounds which have a higher carbon content than cellulose. So you basically extract things that are adsorbed onto your cellulose. Why is it important? Well, if you just make your cellulose nanocrystals and you start doing surface chemistry on it, you can get results anywhere from no modification to very high modification. And we had that, and none of our results, when we started doing surface chemistry of cellulose, were reliable, were reproducible, until we started doing extractions before we did our surface chemistry. We do it with ethanol that, from all the solvents we tried, gave us the best results, and then we got closer to pure cellulose. But this is not really pure cellulose yet. Yeah? You still have more than 1% of carbon missing. What did we extract? All kinds of compounds. So you have the compounds that you would expect from acid hydrolysis. And then you have these aromatic compounds that you extract as well. We first thought this was maybe residual lignin compounds. But we took bleached cotton. We then bleached it again another 4 times. And then did acid hydrolysis. And we still got compounds like this. So we don't really believe it would be any residual lignin, because it should be out. But you can get these aromatics also from condensation under high acid concentration of glucose rings. So these might actually be formed in situ under at 64 weight % sulfuric acid. So very important to do oxide extraction before modification. But then we still have this problem. We don't have pure cellulose. So what could that be? Well, we know that the surface energy of cellulose in air is higher than the surface energy of water with air plus the surface energy of water cellulose, or the interfacial energy of water adsorbed on cellulose. So that basically means that if water adsorbs onto the system, your Gibbs free energy of the system is decreased. And so, can we prove that? Well, if you do a TGA of CNCs, which you just freeze dry, it should be completely dry. You determine, you put them on the TGA and you heat it up. You see that you get a decrease anywhere between 3 and 6%, depending on the humidity, the temperature, and the environment. Same with elemental analysis. And if you do the calculations from elemental analysis, so you correct these values for water content, you get again roughly the same values. So the elemental analysis and the TGA match up. That this difference here is due to water adsorbed on the CNC surface. That is just water adsorbed, just environmental moisture that adsorbs onto your CNCs. So it's important that any time you do elemental analysis to determine the purity of your CNCs, or when you do surface chemistry to then use elemental analysis to determine your degree of grafting, that you also run a TGA to determine your water content on your CNCs, because that will also vary with your degree of substitution. And then you get results that are very accurate and come very close to what you would expect. So that's basically the adsorption of water. So then we wanted to look at the interactions of CNCs with other compounds, and for that we use titration calorimetry. So you have a reference cell where you have a CNC suspension, and you then have a sample cell with CNC suspension, and you titrate in different compounds to look at the interaction. And if there is an enthalpy change on interaction, you will measure it. With every injection, you get a peak, which is either endothermic or exothermic, depending on the interaction. And then you do it to saturation, and then if you integrate the different peaks, you get this kind of curve. From the difference in height, you get your change, your overall change in enthalpy. From the inflection point, you get your equivalence point from which you can get your Gibbs free energy of interaction, and then you can calculate what your entropy of interaction is. So you can get all the values of your thermodynamic interaction results. So we did that for a whole bunch of different compounds: proteins, polymers, nanoparticles, ions, and we also reviewed everything that was done in the literature. And if you plot that on an enthalpy-entropy graph, first time my student showed me this, I didn't believe it, right? They all fall roughly on a line. So then I asked them, well, can you fit this? And the slope of this line is around 298 Kelvin, because this is basically what you're plotting. Delta H is your enthalpy versus delta S, which means that your slope is your temperature and your intercept would be your Gibbs free energy change. Most of these experiments are done at 25 degrees, 298 Kelvin. So that means that this actually matches. It seems that interactions on the surface of CNCs in water environments always have the same Gibbs free energy of interaction, around minus 23 kilojoules per mole, right in the middle of what we got from simulations. So that means that these interactions, that we always get the same change of Gibbs free energy. That means that your strength of interaction always stays the same. What you can control is the selectivity of interactions, the enthalpy-entropy difference. Entropic changes are non-selective, enthalpic changes are selective. And we see that here too. If you look at the points here, where you have a very large negative enthalpy change, these are proteins with cellulose binding domains. These are normal proteins. You have polymers. Here you have ions. You have nanoparticles somewhere here. But even going from ions all the way to proteins, the change in size of these things that interact with CNCs are, it's a very massive change. And this is why it's called an enthalpy-entropy compensation mechanism with a constant Gibbs free energy change, and these things are very standard, or they happen a lot in natural systems. And one of the reasons for this to be so constant is because of the water. So if we now look specifically at some of these interactions, this is one example where we had bovine serum albumin interacting with positively charged CNCs, where we find that BSA binds to about 100 pyridinium groups. So we grafted CNCs with pyridinium charges, so positive charges. And the amount of BSA that absorbed, so this is the degree of substitution of our positive charges. This is the amount of BSA that absorbed. It's pretty linear dependence, and then if you calculate how many pyridinium groups it interacts with, you get to roughly 100 pyridinium groups. At that point, I hadn't looked at what the BSA structure is, but BSA has 99 carboxylates in its structure. So it's from that you would think, and then if you calculate the surface areas that each BSA protein takes up, you get to these values. And so it seems like if you have Very little degree of substitution of positive charges. Your protein is very bungled up and sits closer because there's more groups it can interact with. If you have very low degree of substitution, the protein would need to spread out a lot more to be able to interact with the amount of pyridinium groups. And so we tried together with, again, Gibbs free energy is always roughly the same. So we tried with Yu Ogawa at CERMAF to AFM map these CNCs with BSA adsorbed on it. So if you have a degree of substitution of pyridinium groups of 0.35 and 0.9, what you see is if you map this, you get here a much longer and a less high change, whereas if you have a very high degree of substitution, the proteins that sit on there seem to be much more bungled up. It's not conclusive proof that it actually happens, but it seems to all point in the same direction. So we're still trying to get some other methods to get this more accurate or more conclusive. The same if we take CNCs, and just here they're negatively charged, so we did this with sulfated CNCs. We also did it with carboxylated, but now here I present the sulfated CNCs, either in protonated form or in sodiated form. If you titrate in divalent cations, in this case calcium, you basically get up to a point of saturation, and all of a sudden your baseline goes up very fast. The reason for that is that you get gelation, so the stir that you have in your system starts putting more energy into your system, and basically your baseline goes up because of gelation. So it's a very good way to determine the critical aggregation concentration for gelation, because it's very accurate. Again, the Gibbs free energy of interaction is roughly the same for all different functionalities. So it is, again, the interaction of, and that's something difficult to get your head around it, the interaction of negatively charged CNCs, or the negative charges on CNCs with positively charged ions. The irreversible interaction, so the fact that they keep interacting, is entropy driven. It's not because of the charge differences. You need the charge differences for them to come together, but the irreversible interaction is driven by entropy. Then if you determine the critical ion concentration for CNCs with sulfated groups, it's 1 to 2, so it follows basically 1 calcium 2+ interacts with 2 sulfate groups, so it's very nice. With carboxylates, is a 1 to 10 ratio. The reason is that carboxylates can also hydrogen bond with other carboxylates, so you need less of the divalent cations. They bring them together, and then some of the carboxylates can interact with each other. And very interestingly, we were hoping that if the size of the cations changes, that the entropy of interaction would change, but we don't see any major difference. All the results are within the same order of magnitude, are roughly the same within the margin of error. Although, when you make CNCs which have sulfates and carboxylates on the same surface, you do get a change in the critical aggregation concentration that you need, and you do see that your gel strength and your gel point will change. So if you have a surface with 2 different functionalities, that means that the water structuring over your surface is not going to be homogeneous. Water will interact different with carboxylates as it interacts with sulfates. That means that your water structuring on your surface of your CNCs is going to change depending on what surface functionality you have close by. So that structuring is constantly changing. And apparently that has a very important effect on the size of the ions that interact are going to have a different effect because they will interact with a larger or a smaller surface area. If your surface structuring of your water is homogeneous over your whole surface, it doesn't really matter if it interacts with a larger surface area or a smaller one. So with this, with different surface functionalities, we can now start changing the gel strength of these gels by simply changing the ion that we have interaction with. With monofunctional CNCs, you cannot do this. And it's very interesting to see how these things can actually be used. Okay, so if you look at dimensional variations and surface functionality, we made CNCs roughly with very similar average lengths and cross sections. from cotton and from wood. But what we see then, if you let them phase separate at the same concentration, 3.5 or 5.5 weight percent, you have different amounts of chiral nematic phase in them. Here are the data. So yeah, the lengths are very similar. Aspect ratios are similar. Surface charges were similar. So we see that relatively small variations in particle dimension and surface charge have a different effect on the macroscopic behavior. If you then start determining the diffusion coefficients, so rotational and two of the translational diffusion coefficients, you also see very large differences between the two CNCs. So it seems like if you even have small changes in the average length, it's actually your polydispersity that governs it. Because we'll see later that actually the larger particles, so if you have more large particles, they govern your alignment of your CNCs. And that is, so if you have a wider polydispersity, it has a large effect on your kinetic behavior. So it's not just the average dimensions, it's actually the polydispersity that governs most of these differences. Then if you look at the transition between the isotropic and the cholesteric phase, and with that kinetics of self-assembly, we took 5 CNC suspensions at different concentrations, which looked isotropic, or were isotropic to the naked eye. So there was no phase separation. If you shake them under cross polarizers, you see alignment of the CNCs, and that's what you would expect. If you start shaking them, they start aligning, and you get alignment already at much lower concentration, where before you wouldn't have that. If you take these suspensions, which to the naked eye look isotropic, and you do small angle X-ray scattering, and you look at the structure factor, you actually see that the peak appears already at 2 weight percent. So there is alignment of CNCs in the isotropic phase. Otherwise, you would not see this occurring. So you would have a system where you have these aligned domains within an isotropic phase. At 2 weight percent, this distance between the two CNCs, or the distance that you determine by SACS, 80 nanometers, the Debye length, if you calculate it from the ionic strength, is between 2.5 and 6 nanometers. That is a big difference. So it's not just your electrostatic interactions that govern this alignment of the CNCs. Something else is happening. We believe, and people in colloid science have based on calculations, that this is because of entropy effects, because if you have an isotropic phase, as you concentrate it, the CNC start, or rod-like particles will start seeing each other. If you have then a couple nanoparticles aligning, it creates a lot more entropy, or gives a lot more degrees of freedom for all the other particles around them. That means which particles, if you do the thought experiment, which particles would free up the most space is the largest particles. So you would expect that the largest particles are the first ones to align, because they would have a bigger effect on the degrees of freedom of all the other particles than small particles, simply because their excluded volume is the largest. So you can determine that if you look at the diffusive behavior. If you have rods, they can diffuse along the length of the rods, they can diffuse perpendicular to the rods, or they can diffuse rotational. And by depolarized dynamic light scattering, you can actually get your autocorrelation function, which you then fit, and from that fit you can get your diffusion coefficients. We have published this, so for the mathematics you can go there. But if you measure the diffusion coefficients with increasing concentration, you see that your CNCs, your diffusion coefficient, this is a translational one, this is the rotational one, but you see that your translational along the length axis of your CNCs actually increases roughly at this point, where you do get where you start getting more alignment of your CNCs, which is again in line with the entropic alignment of your CNCs, which gives more degrees of freedom for the other CNCs. You can also see this alignment if you take CNC suspensions, where you have a chiral pneumatic phase and an isotropic phase. So these are CNCs at 1 and 3 weight% were isotropic. At 5 weight% you did have macroscopic phase separation, and so we also measured 8 and 10.8%. This is your just your scattering profile at 1%, 3%. You see that there's a peak or a little blob appearing there. If you take the structure factor, it's a little bit clearer, but you already see alignment. But here, the bottom phase is the chiral pneumatic phase, the upper phase is the isotropic phase. What I actually see is that you do get alignment in both your chiral pneumatic and your isotropic phase. So you do have also aligned domains in your isotropic phase that must be in equilibrium with your chiral pneumatic phase. But what is for me the most remarkable is that the point or the separation distance that you measure in your isotropic phase is the same as in your chiral pneumatic phase. That means that the tactoids that exist, the aligned structures that exist in your isotropic phase have basically the same structuring as your chiral pneumatic phase. So they are in dynamic equilibrium. There must be tactoids going into your chiral pneumatic phase, coming out of it, and you have to have that interaction. And the structuring is relatively the same because their separation distance seems to be the same. So that raised a lot of questions, and then I was very lucky that I had a colleague who started working with us who does photonics, and so we started looking at chiral pneumatic phase structuring. And so he's an expert in second harmonic generation spectroscopy, and so you can also apply that to microscopy. And how does it work? You have a laser, because most people that do this, they like to have laser toys. At a certain wavelength, you can shoot it at your sample. Normally, what you can do for imaging, you shoot your laser, you activate your material, and then you look at the response. If you do second harmonic generation, what you do is you shoot 2 blasts within very short time of each other, like femtosecond time from each other. They will impinge at the same spot, roughly at the same time. They will promote itself, and then the image that you get is based on the combination of the two, and you get a second harmonic effect. Of course, they always try to do it. You can even get the third harmonic effect, which allows you to look at different systems. Now, why is that important? Well, if you look at a 1-photon occurrence, your 1 photon goes through your sample. You do have a focal plane, but you basically see everything from here. If you have the 2-photon effect, you can actually see the 2 photons will reach 1 point in your volume at the same time, and so they will only reach that point at one specific position. That means you have an inherent confocal effect. But you don't need any tracer molecules. You don't need to put any fluorophores. You don't need to put anything in there. You just use the 2 light pulses that hit each other at the same time. So we did that. You take a CSC suspension in a cuvette. This is not a very clear image, but that's the best we could take. If you look at the isotropic phase at the top, that's an 8 weight% suspension of CNCs from cotton. This is isotropic. Here you see the tactoids, the alignment of the tactoids in your isotropic phase. So you can image these tactoids in real life, in real time, in your isotropic phase. What is one thing I should have mentioned is that second harmonic generation is specific for ordered structures. Anything that's not ordered, you will not get an image from, because the scattering is in all directions the same. In a structured system, there you will get specific images, and here you see certain parts that are lighter, certain parts which are darker. So here you see a tactoid. If you then do the same for the chiral pneumatic phase, this is what you get for the chiral pneumatic phase. Now, this looks very similar to what you get from polarized optical microscopy, but this you can do inside your sample. Right. So this is the bulk CNC, not just the surface where you can have surface effects of whatever cuvette you're using. So this all looks pretty. These are nice images, but is this really the ordering of the CNCs, or am I just telling you something? Are we just seeing something and we see this, we want to believe that it's this? So can we prove this? So if we have our laser beam that goes through our material, our laser is polarized. We have our focal point here, and then we have our chiral pneumatic phase. So you have to imagine that this sits here, but if I actually place this here, there's no way you can see all the angles. And so you can polarize your light, so that's your alpha, and then the orientation of your chiral pneumatic director. So here you have your chiral pneumatic director. So the position of this point is governed by your angle theta, and your angle phi is this position in polar coordinates. And then your angle psi will basically tell you in what direction your CNCs are pointing. So it means that our system, the chiral pneumatic phase, is determined by two angles, your phi and your psi, and your linear polarization of your light is governed by your angle alpha, so the polarization of your laser beam. That basically means you can use the laser beam, the polarization of the laser beam, to start probing the directionality of your chiral pneumatic phase. So here you have your chiral pneumatic phase, you have your the direction that your CNCs point in, so that's your change in your angle psi. If you have your particles perpendicular to the beam or aligned with the beam, you would expect that if they're aligned with the beam, so the psi is 0, you don't have a lot of interaction, and you have a dark spot. If they're perpendicular to the beam, you have a light spot and you get lighter image. That's what you would expect, and that's what we wanted to believe. You can actually prove this mathematically by changing the linear polarization of your laser. You then look at the intensity of your signal that you have here, and these are basically the data points. You change the linear polarization of your laser, you look at the intensity, it goes towards 0, it goes towards maximum, towards 0. These are the light areas, so the areas that are here light. These are the dark areas, the areas where it's dark. This is for an angle phi. So you basically, and the red line is basically the mathematical fit for second harmonic generation. When your alpha and your phi are aligned, you get the maximum signal because your cosine becomes closest to 1. Cosine of 0 is 1. When alpha and phi agree, you get the maximum signal. So it basically means that we can actually prove that the alignment that we had here is really due to the fact that you get the lighter and the darker bands within your chiral pneumatic phase. You can then look at a picture here. This is very nice. It looks like a real fingerprint pattern that everybody says. We have a real fingerprint. And then we basically, are going to look here for an angle phi, which is 90 degrees. You go through here. This is a signal you get, which corresponds to this alignment. If you then take an angle of 60 degrees, you see that this shifts. You still get this alignment, and you see that it actually matches in all the different angles that you have. So you basically can use your polarization of your laser to completely probe the alignment of the chiral pneumatic stacking. So in this case, it's aligned in this way, in that way, in that way, then it's in that way. And you can actually prove mathematically that is indeed what is happening. So that means that in every point within your volume, you can now start probing in what direction the chiral pneumatic phase is pointing and what it looks like. There you assume perfect alignment of all the CNCs. We work in a system that's not perfect. So what do? You take this CNCs. You see, very interestingly, something we still are working out. You see grain boundaries here, with which you can do all kinds of fun stuff as well. But now we look at this alignment, And we look at the fitting of your psi angle. So that is the alignment of the CNCs in your chiral pneumatic phase. The blue is the ideal case. The dotted line is what you actually measure. And what you see is that this doesn't really perfectly match to a perfectly aligned system. So you do get some misalignment there. So what you expect is that you get something more like this instead of the system that normally everybody draws. Now we have the data. Can we determine what this is? So yes, you can actually go through the mathematics and allow for some standard deviation in the two different directions. You can then apply that mathematics to the different alignments that you have. And if you do this, you actually see that you have here variations anywhere between 20 and 41 degrees from ideal case. So not only can we look at the CNCs, we can look at the alignment of the chiral pneumatic phases, we can look at in what direction they're pointing, we can even now start probing misalignment and natural deviations from the ideal case of these CNCs in situ. And for that, we can actually map. So because it's confocal effect, we can raster scan it. And this is for CNCs 8 to 8%. You have different planes. You can start packing these planes together. And you can create 3D images of your chiral pneumatic phase. And because we have all the cuts now of this, we can do all the mathematics at every single point within that 3D volume. We didn't use a single tracer molecule. So it didn't affect the system. The system doesn't even know we're looking at it. Well, at least not on the scale of the effect we have. And so within one plane, you can do the Fourier transform to look at the chiral pneumatic pitch. You can do this calculation, and then you get a certain value. The only problem with that is you don't know if the pitch is actually directed perfectly perpendicular or aligned with your CNCs. And normally what people will do is they'll start tilting the stage, but you might actually affect your suspension. But we don't need to do that. We have a 3D volume. We can do a 3D Fourier transform. I'm talking about this easy. It took about 2 months for a mathematician to sort this on how to do this. But we can actually determine now the chiral pneumatic pitch in 3 dimensions. And we can look at the variation of the chiral pneumatic pitch in 3 dimensions. So this is a more accurate value of the pitch than you can get from 2D measurements. So to conclude, we need a lot more knowledge on the thermodynamics and the kinetics of self-assembly, because actually what this proves, what my talk proves, is that we know very little and there's still a lot of points to figure out. Don't forget entropy. It's actually the biggest driving force for most CNC assemblies. Most of the people, and we too, always try to change the surface chemistry to act on the enthalpic interactions. It's actually the entropy that governs most of it. The robustly assembling systems can give significant variations, and polydispersity is key, and that's something that's very difficult still, because most physics models have a large difficulty to cope with polydispersity, because it makes all the mathematics much more complex. We need better characterization techniques and analysis techniques, and now we're actually using our second harmonic generation microscopy to look at CNC structures in various media, and we have all kinds of results now under different salt concentrations and salt conditions on how the structuring changes. We're looking at the kinetics of tactoid merging, and we have some movies where we have 2 tactoids that we actually see merging into one, but we're trying to get the mathematics sorted and see how that relates to the kinetics, but that's very exciting. So finally, this is my group and people I've worked with that I have to thank, of course. And thank you for your attention.
Thank you so much, Wim, for the very insightful talk. I really enjoy it. I would add one topic to your conclusions. Let's don't talk about hydrophobic interactions or forces, but hydrophobic effect.
Yes,
I always
indeed.
tell the same. I have a question while you think on your questions, but going back to isothermal calorimetry, one thing that we found, also as engineers, that you can predict the critical concentration for phase separation maybe in half an hour, as opposed to days that you need. And what we did was to use isothermal calorimetry to see the heat evolution. And that really points out to the concentration that we call critical concentration, right? So it seems to me that what we're doing in the isothermal calorimetry is to detect the early formation of tactoids in the isotropic effect. So now I found the explanation there. Okay, questions? And I love the some frequency generation work. That's really amazing. Yep.
Thank you for the very insightful talk. It was very thought-provoking for sure. I have maybe two questions. One from the first section when you were talking about the delta G being almost constant in all scenarios after the molecules have interacted with the surface. Does this imply that once something is attached to the surface, how strongly it's attached is the same no matter what it is?
Yes, in water. And the way you can actually imagine that is anything that absorbs and your surface, they will be interacting with water molecules around them before they absorb. So as it absorbs, what actually happens is the molecule will attach to the surface. It'll start interacting with the surface. All the water molecules that sit in the plane in between them will be released. So they're losing all their interactions with the molecule and with the surface. And they also gain their entropy. If you have to pull it off, you basically have to do the reverse again. Things that interact better with your cellulose or more selective with the cellulose will be, or you can expect to be more like cellulose, like the cellulose binding domain specifically. So that means that these interactions that they have with the water molecules will be different from, for example, hydrophobic species. And so whatever you gain there in entropic interactions, you will lose in entropy because the water molecules will be happier to interact with them than with the hydrophobic plane. And so it's actually the sum. We normally tend to think of just the interactions of the adsorbent and the surface, but you also, because water is there, we can't forget about the water molecules, and they actually have a very large effect. And it's you have to calculate the effect on all the species that partake. So the way we think is normally in a vacuum.
Fair. I think I understand it now. It's a very interesting concept. And I think maybe the second one is from the second section when you were imaging the chironomatic structure. Are those, maybe I didn't catch this. Is this a static measurement or it's dynamic? And if it's dynamic, how are you correcting, I guess, what the movement of the tactoids in suspension?
Well, yeah. So you basically you basically probe one point in your volume, and then you raster scan in that one plane. Then you go to the next plane and you raster scan, and so you do that for a whole volume. That basically means that the bigger volume you want to probe, the longer it takes. It's kind of like AFM measurements on your surface too, right? The faster you scan, the lower your resolution is going to be. So you're trying to play with that. If you want to make dynamic movies, so you want to actually look at things moving, you try to get your volume or your area within your plane that you look at as small as possible, so you can go as fast as possible. And you are limited to some extent by the kinetics of your scanning to be able to look at these things. Also, to find the tactoids, it takes a little bit of time because initially, well, you try to probe it as large as possible, and then you zoom in on the one spot and you hope that there's still a tactoid there. But it actually, once you have, once there's a PhD student with the right skills, they can become very good at it. And then once you have it, and of course, yeah, you look at one tactoid, and then you scan for a while, and then you must kind of hope that a second tactoid is going to come along to actually see it emerging. But we've been lucky in that regard that we have had occurrences where we can look at how they merge. And it's very interesting to see they have done. They have their pitch lines, so the fingerprint pattern, and as they merge, you actually see that the fingerprint patterns are starting to align. And it's really cool, actually. But I don't have those, well, I don't have the videos yet.
A question here, Wim, from Scott.
Very nice presentation. With your absorption data, do you ever add any type of like chaotropic agents or cosmotropic agents to try to change that structuring of the water to see how then things deviate?
We have tried urea, which is yeah, and in old physical chemistry measurements, that's like the one that most people use. The difficulty with a lot of these chaotropic agents is that they also will interact with your surface. So yeah, we still need to do a lot more work on that. But it is something that we have done some measurements, but the interaction of your chaotropic agents with the surface is also an issue. So it's
maybe moving that question but around. We were visiting Tetsuo Kondo, who has this counter collision instrument that supposedly breaks the crystals or the fibers in the middle plane so that you expose the inner parts and you go against the van der Waals forces that hold the crystals together, right? Presumably, those nanomaterials are hydrophobic or have stronger interactions with hydrophobic solvents and molecules. And I wonder if you have checked those aqueous counter collision materials that can be quite interesting to compare against the regular fibrils.
yeah, that would be interesting. Yeah,
But you know what I'm talking about?
Yeah. We haven't looked at them, but that would be interesting. But then, of course, if you suspend them in water, the chances that they'll aggregate, because that's also one thing that I haven't talked about that we're still trying to figure out is when you do Sachs measurements of CNCs, we know roughly what the cross section is, but when you do the Sachs measurements and you actually fit a rectangular cross section to it, you always have one dimension, which is a lot larger than the other dimension, which doesn't make any sense. And the only way you can have that is if you have some CNCs that would align or stack next to each other with their hydrophobic planes, you would expect. But what we also found, if we do it as a function of salt concentration, the salt does not affect it, which normally you would expect salt to affect the entropic driving force, but we don't see any salt effect. So that's still something that we also need to look at.
Yeah. So for the non-experts, really, we need to look into water. That's so important. And we need to think about what Jacob Waller and others claim. I saw him in one of your papers, that hydrogen bonding is not in charge of everything. And actually, we were in Chengdu conference, and the Chinese community, the French and Swedish community is pretty strong in that direction. Hydrogen bonding is not the reason to hold these materials together. It's actually van der Waals forces. And that's very interesting for us to think. More questions? Yep.